Hello. In this video, we have a special grudge match, mineral acids versus carboxylic acids. Three of the most important strong mineral acids used in the laboratory are nitric acid, sulfuric acid, and perchloric acid. We now know that a requirement for an acid, either as an Arrhenius acid or a Bronsted-Lowry acid, is the presence of hydrogen. But originally this was not known, and it was mistakenly assumed that oxygen was required for acids. And notice how often oxygen is present in the most commonly used acid. This mistaken belief became so prevalent that the word used in most languages for oxygen actually means acid former, which is a mistake. In aqueous solution, nitric acid dissociates completely, it breaks up completely into H plus and NO3. This NO3 minus ion is called nitrate, and we say that nitrate is the conjugate base of nitric acid, just as we say nitric acid is the conjugate acid of nitrate. For a conjugate acid-base pair, the only difference must be H plus. Similarly, for sulfuric acid in aqueous solution is a strong acid. It breaks up to give a proton, H plus also this HSO4 minus 1 ion, which we call bisulfate ion. Therefore, bisulfate is the conjugate base of sulfuric acid, just as sulfuric acid is the conjugate acid of bisulfate ion. Our third representative strong mineral acid is perchloric acid, which in aqueous solution breaks up completely to form H plus, a proton, and the Cl(O4 minus) ion, which is called perchlorate. So perchlorate is the conjugate base of perchloric acid, just as perchloric acid is the conjugate acid of perchlorate. These perchlorate ions have been found recently on Mars. First, we are going to draw out Lewis structures for the parent acid, nitric acid. And we notice that in one of the resonance forms, nitrogen has a double bond to this upper left oxygen, and it's singly bound to the other two oxygens. So this oxygen is sp2 hybridized. The nitrogen has a double bond, single bond, and a single bond, so it is sp2 hybridized. This oxygen and that oxygen, having only single bonds, are sp3 hybridized. But we could also, without moving any of the atoms, rearrange the electrons so that now the double bond between nitrogen and oxygen is between nitrogen and the lower left oxygen. So now this oxygen is sp2 hybridized, the nitrogen is still sp2 hybridized, and these two oxygens are sp3 hybridized. A great trick question is to ask about the hybridization of hydrogen. Hydrogen is never hybridized because it only has one s orbitals available. So notice that nitric acid can be written as a mixture or a superposition of two resonance structures. The more potential resonance structures that we have for a particular compound, the more stable we imagine it to be. So we notice that the nitric acid parent is stabilized by two resonance structures. However, when it deprotonates when it gives up a proton to the solvent to form H plus and nitrate ion. The nitrate ion, the conjugate base, we can write as 3 resonance structures. Now in these 3 structures, I've written the bonds as lines rather than an electron pair, just to make it a little easier to see. But we notice that we can have a double bond between nitrogen and oxygen with this, the upper left oxygen, the lower left oxygen, or the oxygen to the right. So we know that we can write more than one resonance structure. The true structure is none of the resonance structures, but some sort of hybrid of it. So we have a averaging out of single bonds and double bonds to get a nitrate ion that is such that the nitrogen-oxygen bond lengths are all identically equal. And we have a trigonal planar sp2 hybridized nitrogen, and each of the oxygens, even though some look like they're sp2 and some look like they're sp3, in the true structure will all be sp2 hybridized. So we notice that the right-hand side of this equation is stabilized by the fact that the conjugate base anion has 3 resonance structures, whereas the parent has only 2. This theme that upon deprotonation that the conjugate base will have more resonance structures and therefore will be relatively stabilized relative to the acid is one of the driving forces of Arrhenius and Bronsted-Lowry acids, and here we see it specifically for the case of nitric acid. Now, please see in Table 1 the gas phase deprotonation calculations for the mineral acids nitric acid, sulfuric acid, and perchloric acid. Now we know that the acid-base reactions are very heavily influenced by solvation. In the gas phase, we have no solvation, but we can use it to understand simply the electronic features rather than the effects of solvation, and also gives us a benchmark on the relative magnitudes of the enthalpy of deprotonation that we'll see with a acid that we know is a strong acid in aqueous solution. Carboxylic acids, the most important of organic acids, have the general structure R, C, oxygen, oxygen, hydrogen, where R is either hydrogen or some kind of alkyl or haloalkyl group. In general, carboxylic acids are weak acids in aqueous solution, so they do not dissociate completely. To the extent that they do dissociate, they give up a proton, as we'd expect for an Arrhenius or a Bronsted-Lowry acid, and our conjugate base has this RCOO minus structure, which we call a carboxylate. We've already seen at least one way to synthesize carboxylic acids. We know that we can oxidize primary alcohols to aldehydes, and then we can continue the oxidation in aqueous solution using permanganate, for example, manganese plus 7, or some version of chromium plus 6, such as chromic anhydride, chromate, or dichromate ion. And then we'll oxidize all the way to a carboxylic acid. Please see the following slides for a more accurate representation of this carboxyl structure, particularly how we can draw this structure as one resonance structure, but then upon deprotonation, we see that we can write 2 resonance structures for the conjugate base, which helps explain why these are so substantially acidic in aqueous solution, even though in general they're not strong acids, such as the mineral acids, but they are much stronger than alcohols, for example, as acids. The simplest of the carboxylic acids has an R group that is simply a hydrogen atom with the resulting formula HCOOH. The common name is formic acid, which refers to the Latin root formi for ants because certain species of stinging ants use formic acid in their stingers. The IUPAC name for this is methanoic acid. The next most complicated carboxylic acid has an R group that is a methyl group. The IUPAC name for this is ethanoic acid, but is commonly referred to as acetic acid. Acetic acid is the active ingredient in vinegar. If we enlarge the R group to ethyl, we now get an acid that has the IUPAC name of propionic acid, but is commonly referred to as propionic acid. The fourth member of this group has an R group that is a propyl group, and this gives us butanoic acid, which is commonly referred to as butyric acid. As an aside, these short carboxylic acids all have very intense odors. Formic acid is the strong smell of the stinger from ants. Acetic acid is the strong smell of vinegar. One way of which we can get is from the excessive oxidation of ethanol. And butyric acid has a particularly foul smell. Now, in aqueous solution, formic acid is the strongest, followed by acetic, then propionic, then butyric acid being the weakest. The main reason for this in aqueous solution is that as the R group gets bigger, it gets more hydrophobic, it is more and more difficult for the solvent to solvate the conjugate base. So solvation is overwhelmingly a driving force in the relative acidities of these carboxylic acids in aqueous solution. But what happens if we look at them in the gas phase? We would expect one of the effects to be that these alkyl groups are electron releasing. They would release electrons into the conjugate base, the anion. Since it has a negative charge, it would destabilize the anion. The more that we destabilize the anion, the less likely we have for the reaction to go from left to right. And going from formic acid to acetic acid, that's exactly what we see. However, as we get larger and larger alkyl groups, we would expect that they would release more and more electrons into the anion and destabilize it further, so therefore these would be weaker acids in the gas phase. It turns out that the effect of the alkyl groups is very, very small, and it's almost entirely counteracted by a polarization effect that as this group gets larger and larger in the gas phase, doesn't cause any problems with the solvents, and now you have a greater region for the negative charge of the anion to be delocalized by a polarization effect. So we see with the longer carboxylic acids a very similar effect in the gas phase to what we saw for alcohols, where we got a reverse effect from what we'd expect in aqueous solution. Now we want to take a look at the effect of electron withdrawing groups. So our standard is going to be acetic acid, which we know is a weak acid in aqueous solution, and absolutely a weak acid in the gas phase. And here we show the parent acid, and then the conjugate base with the resonance stabilization, two different resonance structures between the carbon and the two oxygen atoms. So one thing to note here, not only is it stabilized by resonance, it's also stabilized by the fact that oxygen is a very electronegative element, which does not mind having a partial negative charge. So a point of comparison between carboxylic acids and alcohols is that in an alcohol, the anion is only, the negative charge of the anion is only spread over one oxygen atom, where in a carboxylic acid, it's spread over two oxygen atoms, and remember, oxygen is a very electronegative element. So now let's suppose we replace one of the hydrogens, at least, of acetic acid with a halogen. So let's assume first it's fluorine, so that we have fluoroacetic acid. Fluoroacetic acid is going to be a weak acid, just like the parent acetic acid, and it's going to ionize in precisely the same way. One thing that's different now is, not only is this negative charge resonance stabilized over the two oxygen atoms, and also spread out over the two oxygen atoms, which are very electronegative, we also have a third very electronegative element here, which is fluorine. So since this anion is stabilized compared to the parent even more than acetic acid, we would predict, and we'd be correct, in both aqueous solution and in the gas phase, that fluoroacetic acid is going to be a stronger acid than the parent acetic acid. And see the following structures of calculated haloacetic acids, with the halogen being fluorine, chlorine, and bromine. And we see that the effect of adding more than one halogen becomes increasingly strong. Relative to the electron releasing groups, the effect of the electron withdrawing groups is much more substantial. In fact, so much so that if we replace each of the hydrogens here with a halogen, so we have a trihaloacetic acid, these are now as strong in the gas phase and in aqueous solution as common mineral acids. So we can actually transform carboxylic acids by the presence of these electron withdrawing groups that are the very electronegative elements such as fluorine and chlorine, and to a lesser extent bromine. We can actually substitute a carboxylic acid sufficiently to make it a strong acid in aqueous solution. One of the possible R groups that we can incorporate into a carboxylic acid is another carboxylic acid group, so that we can actually end up with a compound that has a carboxylic acid at each end. We call these dicarboxylic acids. The simplest dicarboxylic acid is called oxalic acid. The next, carboxylate with a methylene group in the center, we call malonic acid. And then the next, most complicated, has an ethylene group in the center, and we call this particular acid succinic acid. We do know that the carboxylate is an electron withdrawing group. So we predict that the presence of an electron withdrawing group should have the effect of strengthening the acidity of the other carboxylic acid. And that's true. So oxalic acid is a much stronger weak acid than most carboxylic acids because of the presence of the electron withdrawing group of the carboxylate. As we increase the size of the alkyl groups in between the two carboxylic acids, the effect drops off, as we'd expect, because in general the effect of an electron withdrawing group is strongest as close to the anion as possible, and as it gets further away, the effect drops off. But again, as we recall from the effect of electron releasing groups in the gas phase, these generally have a much smaller effect than the effect of the electron withdrawing groups. There is one further point with the dicarboxylic acids, that however much energy it takes to remove the first proton, to give up the first H+, we're removing that from a neutral molecule. To remove the second, because these dicarboxylic acids are diacids, they can give up 2 acidic protons. It is always much, much more difficult to give up the second proton than it is to give up the first, because the first proton we're trying to remove from a neutral molecule. In the second case, we're trying to remove that positive charge from something that already has a negative charge. Whenever we have polyacidic compounds in inorganic chemistry, we see exactly the same sort of thing, and this is entirely confirmed by the results in the gas phase. We have one final important electron withdrawing group that we haven't looked at yet, and that is a phenyl group, or a benzene ring, that's attached directly to our carboxylic group. This particular carboxylic acid is known as benzoic acid, and the conjugate base, benzoate, as the sodium benzoate, is extremely commonly used in food products as a preservative. So I encourage you to look at any food that you're eating and look in the ingredients to look for the ingredient sodium benzoate. Now, we expect that the benzene ring will be electron withdrawing, and the results in the gas phase show that this is true. The overall effect of the benzene ring, as far as electron withdrawing effect goes, is about equal to a haloalkyl group. So something like a chloromethyl group. The benzyl group has the benzene ring, the phenyl group, has roughly that effect. So this effect we know is not from electronegativity, it's entirely from resonance. And if we remove the hydrogen here, not only do we get delocalization of the negative charge over carbon and into oxygen, but we can also write numerous resonance structures that involve the benzene ring. Again, I thank you very much for your attention. As always, have a good one. And in honor of the Philadelphia Eagles winning the Super Bowl, fly, Eagles, fly.